Welcome to EasySpin Academy 2020. This is the last session of day 3 where we just going to go over some of the questions that popped up on Slido during today's sessions earlier. So one thing that I found, switch to the MATLAB window here, interrupt the calculations. One thing that somebody asked about in this terbium example, which I showed, how to actually figure out what spin state a particular energy level belongs to. Let's go and pick that terbium example again with the energy levels, bring it out to a clean file and just run it just for our reference. Here it is. Okay. So now, for example, you want to know what are the particular spin states, let's say at 1 millitesla. And what you need to do in this case is you need to set up the spin Hamiltonian for this particular field and then diagonalize it to get us starting to get the eigenvectors. So let's do that. The spin Hamiltonian equals S ham of the terbium system at, let's say, 1 Tesla pointing along the z-axis would be B0, 0, 1000. So let's abbreviate this here as B0. This is the field vector in the molecular frame. Now we've got the Hamiltonian. Let's look at it. This is how it looks like along the z direction. Now we need to get the eigenvalues and the eigenvectors. V are the eigenvectors and E are the eigenvalues of these Hamiltonian. Let's look at them. E are the energies here. You can see the lowest one is minus about 118 gigahertz. Let's see if that's consistent with this plot here. Yes, it is. It's about 1.15 times 10 to the 5. It's the same number of this here. Okay, so we've kind of let's add a vertical line here, X line at 1000. We're kind of going to look at these 1, 2, 3, 4, 5, 6, 7, 8 different states. So one general thing that helps me a lot when I look at energy level diagrams is that the slope of the line tells me about the m sub s quantum number for that state. If it's a very positive slope or a very negative slope, I know it's a large ms quantum number like +7/2 or -7/2. Whereas if it's pretty flat, it's closer to 0, maybe +1/2 or -1/2. Of course, if there's a lot of state mixing going on, this m sub s quantum number is not well defined, right? But even in these situations, you can calculate an expectation value for the m sub s. And let's do that. For that, we need the corresponding operator, which is sz. And sz you can get with just calling SOP for this particular spin system and just saying z. Okay, let's look at this operator. This is the sz operator. It is diagonal. It is diagonal and has, the expected quantum m sub s quantum numbers on it. Now to calculate the expectation value for each of those states, let's look at the state descriptions. So each column in the V result from the eigenvalue and eigenvector calculation corresponds to one state. Let's also plot out the energies. So the lowest energy gives the eigenvector shown in the first column. And then the highest energy has the corresponding eigenvector in the last column. So for example, if you want to get the quantum number for the lowest energy state, what we need to do, we need to pick out, let's call that little v. We're going to pick out the first column, so all rows, first column, and we need to calculate the expectation value of SC. That's very simple. You do V complex conjugate transpose times SZ times V. And that basically is the expected m sub s value for that particular first transition. And it comes out as -3.4, which is not quite -3.5, indicating that there is a state mixing going on. We can go one further up. Let's clear the command window here. And then the next level up has m sub s of -2.28. And then we can increment that using the increment value and run section feature. The third level is at -0.44. I think this is the light orange one. Fourth level is at -1.4, which is actually higher in energy than the the previous one with the lower number, and so on and so forth. And I think the highest number is at plus 2.4. So this is one way to figure out what type of spin state you're looking at for each of these levels. I hope this answers the question. Another question that I thought is useful to look at is how to actually get resonance field positions out. For example, how to plot a roadmap for a crystal rotation. And this can be done using a function that I haven't mentioned before that is called Resfields. Okay, we're going to make a brief example for this. We define a spin system. Let's make it anisotropic. Let's say it has g values of 2, 2, and 3. So it's axial, and it's a spin 1/2 for simplicity. Okay. Now, if you Resfields, you can go look at the documentation, what it does. Let's move over to the documentation. Go to the alphabetical function list. Scroll down to Resfields. And see it's compute CWPR resonance line positions, amplitudes, and widths. And it does that without actually constructing the resulting spectrum. So you can actually get the numbers for the positions and how intense the lines are, and you can process them further in your way if you need them for other purposes. So it takes a system input and the parameters. And the parameters are the same ones: microwave frequency, fields, and temperature, and so on. Okay, so we need to feed it the spin system and some experimental parameters. And I think the microwave frequency is sufficient for our purposes, 9.5. What does it return? We can again go back to the documentation. And the syntax summary for this Resfield function, of which there are several offshoots, depending on the level of theory, is it gives you the position as the first output. And if you ask for another output, you get the amplitudes, and you can ask for more and more granular information about the resonance behavior of the spin system. Okay, we only need the positions for our purposes. So let's call them positions, or BRes for resonance fields, and see what we get. I think we also need to specify a search range, but let's see if Resfields complains. Control Enter. Yeah, Resfield indeed does complain. And this is how a typical error message looks like. The first line shows you where the error occurred, but then the second line actually contains a hopefully intelligible EasySpin error message. So if you get if EasySpin crashes for whatever reason, please look at the command window, look at the red highlighted text, and look there whether there's an EasySpin error message. That will help you track down and see what you can fix. So here it says X range is missing. It needs a search range. So let's give it a search range for the transitions between like 200 and 400 millitesla. If you run this again, voila. Now it found out that 226 millitesla is the resonance. Now, why does it just give one field? Shouldn't it give us a powder? What does it do? I think Resfields automatically assumes a crystal if you don't specify anything else. So let's put in a crystal orientation. We can put that in manually, 0, 0, 0, and we get 226. But now if you turn the crystal by pi over 2, we get a different resonance field, 339. And what we can do now, we can make a series of angles, like a theta angle, and we can make the angle go from 0 to pi over 2, which corresponds to 90 degrees, and then write a for loop. Going to loop over all these thetas from 1 through whatever the number of elements in this theta vector is. And for each time, in each loop iteration, set the orientation to this particular theta angle, number t, from this vector, and calculate, call Resfields, and then store the result in a vector for element t. So this is a for loop, and basically it runs over every element of theta, calculates the resonance field, and stores it in this bres vector. So let's run this. It runs clean. And at the end, all we need to do is to plot the theta angle, or plot the bres field against the theta angle, which we might want to convert to degrees for easier visualization. So if I select this and then press F9, we can get what's called a roadmap. On the x-axis, you can see the magnetic field. And on the y-axis, you can see the theta angle in degrees. So we're starting out, if the theta angle is 0, the magnetic field is along the z-axis of the molecule, and the gz value is 3. So we are at a low field, because high g values correspond to low fields. And as we turn the crystal, and towards the situation where the magnetic field is going to be along the x-axis, basically theta equals pi over 2, which corresponds to 90 degrees here, the resonance line keeps moving up in field until it converges to the g equals 2 position at about 340 millitesla. So this is how you can build a roadmap of resonances. And of course, if you have more than one resonance, you will have to store them all and then plot them all together. Of course, we didn't calculate the complete smooth curve here. We just calculated several theta angles and then MATLAB connected them with line segments. If you just want to see the ones that have been calculated, use this extension to the plot command that specifies how the line should be plotted. In this case, just as dots. And I'm running the code again, and here you can see the calculated resonance line positions. We can also ask Resfields to give us back the amplitudes. Let's do that. Bres, and let's call amplitude and store them under T. And let's make this a separate subplot. Actually, 211 and 212. Let's plot as a function of theta the amplitudes. And let's maybe again press just plot dots. Okay, so on the top again we see the same plot as before, but in the bottom we now see the amplitude dependence of this resonance line. So the horizontal axis is the theta angle, and the vertical axis is the intensity of the EPR line. You can see if theta is 0, the intensity is smaller than when we're at theta equals 90, where the intensity is larger. Now, why is that? The reason is that, if you imagine the z-axis, the field pointing along the z-axis, the static field, which basically corresponds to this orientation here. The microwave field is coming in perpendicular to it, if in perpendicular mode, right? So it would be my green pen here, right? The blue pen would be B0, and the green pen would be B1, the microwave field. So the blue pen sees the GZ value, which is 3.3 in our example here. But the green pen, which is the B1 field from the microwave, actually sees the other two values, the G value of 2. And it interacts with the spin through that G value, not through the G value of the B0 field. Right? So in this situation here at theta equals 0, the microwave field sees the G value of 2. And if you then go over to theta equals 90, so you turn this way, or this way, let's say, so the B0 field is along the x-axis, the B1 field will be along the z-axis. And then it will experience a G value of 3, and so the absorption will be more effective, and that's why the intensity gets larger. So the EPR spectral intensity depends on the G value perpendicular to the static field. That's a detail of solid state anisotropic systems that's worthwhile being aware of. So this is how you get resonance field positions and amplitudes out of EasySpin without actually simulating a spectrum. So I hope this answered the question. Another question that I wrote down here that I saw on Slido was, at what point, how do you assess whether you have a good fit? Well, that's a very difficult question to answer if you do least squares fitting. So there's at least two aspects to it. Well, first of all, you have to decide yourself on what type of model you are fitting to the data, right? So if you have a very broad, washed out spectrum, it's obvious that you can't fit a ton of different hyperfine couplings to it because you don't see any hyperfine splittings, right? So any of these hyperfine couplings you might include in a Hamiltonian, they're completely unconstrained by the data. In this case, the model spin system is too big, it's too detailed, and your data just does not support this model. even if your molecule has these many hyperfine couplings. But if they're not resolved, there's no way you can fit them, right? So, and I've seen this many times that people have overfit their spectra really badly by having way too detailed models, given the bad resolution in there, or the really washed out nature of their EPR spectrum. So, well, what to do in these cases? Just try to go back and see if you can get higher resolved data, if you really want to get those hyperfine couplings. So if it's hyperfine, you might want to do Endor or ECM experiments, or collaborate with somebody who does. Sometimes EPR spectra are insensitive to certain parameters that might even be large energies, like zero field splittings. If you want to figure out those parameters, then it's worthwhile to go to high field, right? You could even submit a proposal and send your sample to a high magnetic field lab, for example. In the US, it would be in Tallahassee, Florida. So the alternative is to trim down your model. So basically give up on those hyperfine values and just replace them by just some generic broadening, like level 0 broadening with LWPP. So that's one aspect. What is an appropriate model to analyze my data? If you have a ton of resolution in your data, there's a ton of information, and you will be able to get a ton of parameters out. If it's not resolved, you just have to use a simpler model. Okay, now let's say you decided on a model, you fitted your data, and the fit looks okay. How do you assess the quality of the fit? Well, first of all, you look at the root mean square deviation between your spectrum, and a measured spectrum, and the simulated spectrum. If the fit is nice, then the root mean square deviation will be very small. And you can also plot the residuals between your spectrum and the simulated spectrum and the noise experimental spectrum. The residuals should be pretty flat. Yeah, but that alone is not a guarantee that your fit is good, right? Even if it looks good, it might still mean that your model is overspecified. It's too big. That still can be the case, right? So you have to use your scientific judgment of whether you're overfitting or not. I think these are the most important aspects. One current limitation of ESFit is that it's not allowing you to look at parameter uncertainties. This is in the works. In fact, it's already implemented on a GitHub branch. Please come back and check out the 6.0 dev versions in the near future. We will have that in there. And once we have parameter uncertainties, that gives you another idea of how well your fit actually worked out. So if you fit a parameter and then the error that comes out is really large, it's going to tell you that this parameter is not well constrained by the data. And you might consider simplifying your model to not include that parameter at all. So those are kind of the most important questions I picked up. If you have further questions, I will hang out on Slido for the next 10 minutes. And after that, I and all the other EasySpin folks will be over at Gather Town in the happy hour. I think it only opens at the top of the hour sharp, so you can't go there before that, unfortunately. But if you go there, just, I think Stefan set up some poker tables, and you can also bring your own beverage. This is the final happy hour of this workshop. If you still have questions that we can't answer here on Slido or in happy hour, please always refer back and come to the EasySpin forum, which you can access this way. You go to the EasySpin website, and then on the top right, there's a button that says forum. If you click there, there is a forum that works permanently throughout the year where you can post your questions. I think that's it. This brings us to the end of the EasySpin Academy 2020. And first of all, a big thanks to Stefan Pribitzer, who has been managing the technology here. It was absolutely flawless. Thank you very much, Stefan. I was unexpected to have 0 glitches. Well, so far, it could still happen, right? Thanks everybody for attending. And I really do hope that this workshop helped you to get a little better understanding of how you can use EasySpin in your research. And I hope to see all of you hopefully soon in person at one of the many scientific conferences where EPR is an important part. So thank you very much for attending. Please join us at the happy hour that starts in about 9 minutes. Bye-bye.